Okay, so the second part of this Module 1 webinar brings together those technologies just discussed, the resource description framework, its schema language, its ontology language, and its query language, and gives some principles for how that should be used in combination with web technologies, and some best practice about how you use these technologies under those principles to especially expose and also increasingly how to aggregate and consume that data to build applications. Okay? The second part of that, the best practice for building applications, is coming up during the rest of the Euclid webinars over the coming months. For now, we'll talk especially about what the principles are, what the best practice for exposure is, and talk about some example applications and a quick history through how these have been built and how they've evolved. So, as I said, when it comes to publication, what we're trying to do is expose data alongside content, which comes from different knowledge domains with different existing vocabularies for how to describe things in those domains, in order that the data is self-describing, so that we can take any resource or any relationship or a group of resources and understand what that means by resolving the identifiers to RDF-based descriptions, using things like the schema and ontology language and query language. As well as being self-describing, there should be a standard means of access, so we reuse HTTP to tell you how to get the data and its metadata, its description in this way, and to make it linked, hence linked data. So a given assertion or a given set of assertions over data can be understood with respect to existing data that's been exposed. So we'll talk about some big data sets. In particular, we'll use them music data sets, geography data sets, bibliographic data sets that relate to those music content, okay, in order to illustrate these principles. Principles are as follows. Okay, I'm going to go through these one by one to say what these mean with respect to the use of the technologies considered in the first half of the webinar. So the first one says, use URIs to name the things that you're talking about. Okay, so on the web, we use URIs for documents. When we're concerned with data, linked data, or the web of data, we have both identifiers for documents, things like RDF describing a resource, or RDF describing a vocabulary. Okay? But as well as those documents, we use URIs for the things that they describe. Because as we said, we pick resources with URIs to model things like the Beatles, okay? Or the classes and properties that we use to describe them. Sometimes it's said that the distinction is that we're not just identifying documents, we're identifying real-world things. But that's actually a bit of a misnomer. We're not just talking about things even in the real world. It's things in general that we agree about and that we can share descriptions of. So there are plenty of things that are not in the real world, like Hogwarts within the Harry Potter universe, that we can agree and give URIs and give descriptions to. Okay? So any shared thing that I care to identify and describe, I'll give a URI to follow the first principle. Okay? The second principle refines that a little bit and says don't just use any old URI from the set that we talked about in the first half or others. Specifically, use HTTP URIs. Why? Because that means we can find out about them. We can make them self-describing because we have a protocol to look up the description. When I use a URI for the Beatles, you look up using HTTP, you go to the authority, you pass him the content ID, so those two components of the URI, and you say, tell me about this resource. Okay? And you'll get back some canonical RDF from the authority about what that resource is, which in general should contain things like the label for that resource and should contain a description, a comment, or an abstract, hopefully in multiple languages. Okay? So whereas we said a DBpedia URI, you can pretty much work out what it's referring to. In fact, you can make the trick and say, well, every DBpedia URI corresponds to a Wikipedia URI. So in those cases, you can get human-readable text from Wikipedia. In general, we don't rely on the URI containing a name for the thing, and we don't resolve to the human-readable web, we resolve to RDF. So we ask using HTTP, what's this thing? Tell me about it in RDF, and it should come back with a name and a description in whatever languages we care to read about it through this uniform mechanism. You use the URI to look up a description of that resource. Okay, so the third principle gives some more guidance. What should you get access to when you resolve these HTTP URIs? Okay, it says provide something useful. Originally it said in RDF or Sparkle. It used to be that the only standard for giving someone RDF was RDF in XML. Okay? Then it became RDF-A, which we'll talk about later, is a valid form of passing someone RDF. So you can put RDF inside HTML as annotations. That's also a standard for giving someone RDF. We're also very close to Turtle being a standard for giving someone RDF. So by all of these means, you should be by some of these means, you should be able to ask, tell me about this resource and give me back RDF, either in itself, in XML or in Turtle, or as part of the web content that you're providing, which you'll see later is actually what MusicBrainz does. When you look up the Beatles on MusicBrainz, what you get back is a mixture of HTML and RDF in this form called RDF-A, RDF annotations. So as well as getting back RDF, the authority on that resource that has been described to you or that you're making descriptions about can provide a Sparkle endpoint where you can query about that resource. Now, in general, you'll see in best practice, while some people try to give you a query interface, perhaps with restrictions, it's not that practical for everybody who wants to model things, who cares to describe resources, to give you an open query endpoint over their data. So best practice here would say, as well as resolving the individual resources, so you can look up a particular resource with a URI, instead of giving a Sparkle endpoint, you might give what's called an RDF dump, which is a wrap-up of all the data they've got in RDF form in a downloadable package that you then can put in some engine, which will give you a Sparkle endpoint. Okay? So either you might find a Sparkle endpoint to query about these things that have been described to you, or you might obtain a dump which you can load into a triple store and make your queries about locally. Fourth principle says, okay, so just to review quickly, give URIs to things, make them HTTP URIs so you can look things up. When you look things up, they should use the standards, RDF and Sparkle. The fourth thing says, what you get back should be interlinked. Okay? So the descriptions you get of the resources of interest can be described to you via their relationships to other people's data. And this is a really important part of linked data. To take one simple example, if I want to attach some biographical information to music, okay, I might give URIs, give identifiers to particular artists and groups, all of the things that we've just talked about, and they might be in relationships with particular countries or cities. Instead of modeling those countries and cities, which are already described in other data sets, linked data encourages us just to use the identifiers from those other data sets for geography. So instead of reinventing what the United Kingdom means or what Liverpool means to put the Beatles in a relationship with Liverpool, I'll put them in a relationship with an existing URI from another data set for Liverpool. Now, when it comes to reuse, there's actually potential to make this reuse, which is encouraged at two levels. What I was just talking about was at the instance level. And the easiest way to do instance level interlinking is by direct reuse. So GeoNames, as a data set of geographical data, has a URI for Liverpool. So I could make a triple that directly puts my URI for the Beatles into a relationship with GeoNames URI for Liverpool. Now, in some cases, I will both give my own URIs to things that perhaps already exist, but I give my own URI to assert my primary relationships with, but I'll use this same as predicate from OWL to say, when I use this ID, say for Liverpool, it's the same as the ID. It's my resource refers to the same Liverpool as the one in GeoNames. Okay? So we've actually already seen an example of this on the fly. When the BBC make music reviews, they mint, that's the term used for creating a URI scheme, they mint URIs for the music artists, but they assert same-as relationships between their URIs for music artists and the ones in Music Brains. Okay? So at the first level, I can directly use someone else's URIs, but I can equivalently, under inference, use my own URIs, but assert same-as relationships. Okay? Now, we also have weaker relationships between instances. So commonly used was see also for look at another document. We can also, both at the instance and schema level, use SCOS predicates for things that are pretty much matches, but not exact same as. So SCOS gives us a predicate for broad match that we can use at the instance level as well as at the schema level. Specifically at the schema level, we might also interlink. So again, going back to the principle, when I talk about a relationship or about a class, I give it a URI, and linked data tells me I should use an HTTP URI where someone can look it up. So if I say the Beatles go in this class, the URI for the class can be used, can be resolved to give my description of that class. Okay? But it might also have some relationship to someone else's schema. Okay? In the best case, someone else's schema already captures what my class is, and I just use their class. But it could be that I'm refining their class, in which case, when you look up mine, you'll see a relationship. My class is a subclass of theirs, another vocabularies that you can look up. Okay? So we have alignment like that based on refinement. In some cases, just like the same as at the instance level, it can be I wasn't specifying something more specific or more general, just that I happened to give a name to a class and then perhaps later found out that someone else has an identifier for the same notion, the same grouping. When I do that, I do the equivalent to same as at the instance level at the schema level with equivalent class. Okay? And everything that I just said also applies to properties. So if I use a property to say, I have certain relationships in my data, okay? You look up my property and I describe it for you in RDF using the schema language or the ontology language. Okay? Using just the schema language, I can say, this is more specific or more general than an existing relationship using the subproperty of predicate. Okay? I can also say, I defined this relationship, but so did someone else, and they're directly equivalent, so I will assert an equivalent property relationship between my property and theirs. Okay? And then finally, to complete that argument, it could be that there's a non-exact. So it's not equivalence, and it's not specialization or generalization. It's just a more or less match. So I might use things like SCOS to say, there's this one over there. What I'm saying is related to that, but it's not exactly the same. Okay. Now, once we have the 4 principles in mind for how to use those technology in the best possible way, we also have a star rating scheme to look at the data that people expose on the web and say, how well does it conform to those principles and best practice? 5 stars is where following the 4 principles aims to get you. Okay? But there are star ratings for people who are part of the way there, who are not necessarily using all of the linked data technologies, or maybe you're not using them all properly. So we get 1 star for just putting data on the web. So if we have somehow a web page about the Beatles, that will give us at least 1 star because we've put something online about the Beatles. If it's resolvable from HTTP, which means if it's on the web. We'll get 2 stars for, at the technical level, the data being machine readable in some way. Okay? Now, what you'll find when people have legacy data is the crudest thing they can do, if the legacy data is on paper, is to scan it all and put images online from scans, or put those images into PDFs and publish, their company handbook, their company product catalog, just as images within a PDF or as images on the web online. That would only get you 1 star. To get 2 stars, it has to be machine readable. Okay, so you at least need, in that case, you need reliable optical character recognition over, so the data's machine accessible, or better, the normal case, you put a database online. Okay, so your database, perhaps a relational database, is being transformed into HTML pages, and the data's there, machine readable within the HTML. For that, you get yourself 2 stars. You get yourself 3 stars by using some non-proprietary format for that data. So no PDFs, no Excel documents, but instead something more open. Okay? So plain text, as open as it can be, a CSV file instead of an Excel spreadsheet, okay, will get you 3 stars. If you want to make it up to 4 stars, you need to identify the things that you're talking about using an open standard. Okay? Ideally, linked data best principles would tell you use HTTP URIs. But other identifiers are available even within the URI scheme. So if you use DocBook IDs, you've consistently used IDs when you're referring to things within your data, you've consistently used IDs, so you get yourself 4 stars. To get 5 stars, you have to link those IDs, link the things within your data to other people's data as well. Okay? So the best way to get 5 stars is to follow the 4 linked data principles. Okay? So 4 stars says consistently use IDs. Linked data best principle says consistently use HTTP URIs as those IDs. Okay? 5 stars says link to other people. Following on that argument, the linked data best principles say easiest way to do that, you use HTTP URIs, other people use HTTP URIs, and you reuse other people's URIs in your data. How do you do that? Easiest way, by using RDF. Yeah? I relate two things that have URIs together under a particular relationship by asserting an RDF triple to relate the two things. Okay, now in terms of people who have exposed their data using the principles and then advertised their data, the working group that was pushing open data in linked data form, called the Linking Open Data Working Group, assembled those data sets together into a simple diagram to start with that looked like this. Okay? Each bubble, each node in this diagram is a data set, okay? Given a name as the whole set of data. For instance, dbTune, that had MusicBrainz data in. For instance, GeoNames, which I just mentioned, and MusicBrainz and dbpedia. And if they were interlinked, so if they shared URIs between them, then you have an arrow saying whose URIs, which datasets URIs you reused. So every arrow in here is an instance, if you like, of the fourth principle, where the other three principles are used to expose the data inside the bubble. In 2007, it was easy to count how many datasets were using those principles. But as the years went by, this diagram became huge. There are many datasets with many interlinkage points between them. So just to draw out a few that we've talked about, you see dbpedia here, very, very, very heavily interlinked too. It has so many arrows coming in that you can't even distinguish them anymore around dbpedia. Okay? So a successful way, it's easy to argue, to expose data sets. You can see simply from these openly exposed data sets that are grouped together in this diagram. And this diagram isn't even counting those data sets that are interlinked and are exposed according to the principles, but not openly, not for everybody's access. One way to understand what's in the cloud now is to color code it based on the broad area that the data set fits into. So you'll see there's a key down at the bottom right-hand side. Probably easier to see if you download the slides than see in the webinar or its downloaded version. But for example, we have lots of life sciences data in this mauve color down here. We have lots of media data, which is where our music data sets are, up here in blue. And there's statistics then to help us understand what's in there. So in terms of this registered and interlinked set of open data, exposed as linked data, we had a count at the time of this last diagram of 31 billion and a half statements. That's how many RDF relationships there are between resources. And those are divided into nearly 300 data sets overall. And the pie chart shows, according to that color coding, which of the domains are more prominent in terms of open data there. So you see life sciences is quite a large proportion of that, but media, which we'll look at, is a significant chunk too. In terms of the interlinkage, that's how many links there are from each data set into other data sets. We have the order of about 500 million interlinks. So we can see that that fourth principle that says don't reinvent things linked to other people's descriptions is also really successful in this domain. If you do the analysis there to say in which domain is that outlinking to other people's data sets the most successful, you see that things turn around a little bit and you get government data, which has been, by its nature, the government data that's getting exposed is open data. So the push to make that kind of open data into linked data has been very successful if you measure it in terms of how interlinked it is. And that's really useful for studying government data, so you can understand what's in there relative to existing data sets when new data sets come out. Okay? Similarly, geographic data, very heavily interlinked. And that's very useful if you want to, as I said, describe your resources, even in another domain like music, resources like the Beatles, to tie it to geographic linked data. Okay, now in terms of exploiting that masses of linked open data, there's many useful applications that can give us inspiration for how to form applications over linked data in general. The first class, called linked data browsers, one can agree or disagree whether these give a useful tool in themselves relative to all of that linked data. So the idea is to look at the data and give a web browsing-like metaphor for exploring the data itself. Okay? So you turn things that are exposed in the data and well-understood classes and properties into a human-readable or semi-human-readable representation in a browser. So just as one example, a commonly used property is faux depiction. So faux tells us if you want to depict something in a bitmap, we have a standard predicate to let you make that link between the resource and a bitmap depicting it. Okay? So a linked data browser will say, if you want to look at a particular resource, you can give its identifier, we'll find all of the data that we can about that resource and represent it, including when we find it related to a bitmap through this depiction property, we'll put that bitmap on the page. Okay? When we find a label, we'll use it as the title for a page. When we find a comment or an abstract, we'll give that text as part of the page. Now, as I said, that may or may not be a useful way to explore data. It's not very end-user friendly. They're not the nicest looking tools. And part of the reason for the principles being the way they are is that you can set hand-created, or at least machine-created, oriented towards humans, human-readable content alongside data content. So when that's done consistently, there's no reason to turn the data into human-readable content because it's alongside human-readable content in the first place, and that's what should be being browsed. The data is there to be aggregated. On the other hand, in terms of giving visual metaphors for aggregated data, there are things that we can learn from the linked data browsers. Okay? So one popular one, after very early projects like Tabula, was called Marbles. And it's called Marbles because when it collects a piece of data to display, it displays it with some visual representation of the provenance of that information, where it came from. These little colored dots in this browsing view, each called marbles, the color represents from which source, from which data set, that data that's been represented comes. Okay? So when we see there's a resource that's labeled Tim Berners-Lee that has a depiction with this bitmap, we can see from these two marbles that that is a depiction of that resource according to those two among the data sets that have been aggregated. Okay. So that can be useful to give a visual metaphor for data aggregation. There's something to learn from that tool. Another quite early tool that gives us a metaphor or an archetype for tying together linked data with another paradigm, which is user-generated or user-sourced review information, very common part of Web 2.0, was review.com. Okay? So like Yelp, like TripAdvisor, like many of these review sites, Amazon, you have a visual depiction for how to represent yourself as a user and give your opinion on something in the form of a review. What was distinctive about review.com is those things on which you were giving opinions were identified as linked data and had metadata available in RDF, having been identified with the URI. And your review is adding to the metadata. So when you submit a review, you're identified with the URI, your review is identified with the URI, and it's associated with the URI of the thing that you have reviewed. So this means to bring together reviews with linked data, a really useful paradigm, really useful metaphor, and one that we'll explore when it comes to music reviews in the motivating scenario for Euclid in later webinars. I mentioned earlier interesting use of linked data is to tie together content, human-readable content, that's available in different ways. So back in the early days of the web, the assumption was that you'd have a web browser on a desktop machine, more or less. In intervening years, we've both moved to more mobile, dedicated computing hardware, like a notebook, into carrying around computers with browsing capabilities all the time, like mobile phones, like tablets. Okay? In this reality, where we have all of these different screens to look at content, linked data gives us a really useful way to both encode and aggregate what the underlying data is and the underlying metadata for your content when it's represented in different ways. Okay? So you have these different mobile interfaces, tablet interfaces, app interfaces, as well as traditional browser-based interfaces. And all of them are tied together by representing things that have linked data principled representations. Okay? So even though you have different interfaces, things have common URIs. Things have RDF to describe what's represented on a page. Now, some of the technology that ties together these linked data principles with these interfaces can be seen in an interface like DBpedia Mobile that said DBpedia has all of this RDF represented data that comes from Wikipedia info boxes. If we want to form a different interface over the top from just the web browser interface that DBpedia itself gives, we can use a lot of the properties of the data itself to build these kind of interfaces. So, for example, we looked really quickly earlier at how we represent geographic data about resources, that we can attach latitudes and longitudes in a common vocabulary to those resources. Now, when your data has that, you have URIs for things that have geography and a common way to express what their latitudes and longitudes are. You can aggregate that data towards a mobile interface for mapping, for instance. So every resource you can turn into a pin in a mobile interface to mapping, and each one having an identifier, you can then browse to the metadata that's associated with that particular resource. Okay? So we extend this idea of the linked data browser giving a generic way to look at the resource in itself, and also have metaphors for aggregating those resources, for instance, via their geography, into a common interface for mapping. An interesting tool that takes up the provenance-oriented ideas in a more modern user interface would be Sigma, which mashes up, which allows you search interfaces, search, faceted search, many of the things that we'll talk about as advantages of semantic technologies, together with this visual representation of provenance, So we can find out not just what's known about Tim, but who says that certain things are known. For instance, his location, his age, all of these contentious things that we might assert. Now, in terms of using linked data for existing content, a nice example is the New York Times subject index. They had for a long time, even pre-electronic exposure, they had a paper catalogue of all of the taxonomy they used to organize journalistic content into different subjects for articles. Now, they, at the same time, turned their subject index into RDF via SCOS and expose, using the kind of annotation to web content that we'll look at later, what each story has, what it concerns relative to that subject index. Okay? And the microdata in pages that's used for that annotation can be used across news sources. So this gives a useful way not just to find your way through New York Times content, but through other journalistic content as well relative to their subject index. In the same way, and this is something that we will come back to as we build our motivating scenario, the BBC annotate their music-related content, in particular their music reviews, which they write or commission. The way that they expose those music reviews is by interlinking using MusicBrainz IDs. Okay? So again, by having common identifiers for things like artists, albums, singers, publishers, record labels, we can bring together the BBC content with other people's content in novel ways using those linked data principles. On the geography side, as well as data sets that are created to be exposed in that linked data way, we also have projects taking open data and exposing them using linked data to allow mashup. So just to mention one, we have linkedgeodata.org, which is taking OpenStreetMaps data, openly crowdsourced mapping data, and exposing it in linked data-like ways. Okay? And immediately you do that, not just do you have a route to easily draw mapping on top of that, but to do aggregations with other data sets and have aggregated mapping, the way that we've talked about a couple of times. When we talked about data sets and representation, we said that government data have become quite a big source of linked open data. So first with data.gov represented here, and then in other countries, so for instance, data.gov.uk in the UK, also in countries like Spain and Italy so far, there's a heavy push towards using linked data technologies for open data. And at sites like data.gov and data.gov UK, you can see these common metaphors for aggregating data together and building user interfaces are exposed first class as well. So you can go and look at the mashups that are built on top of data.gov UK data within the site and see how other people build applications on top of this data. So to summarize what we've looked at throughout this webinar, we looked at the basis for these technologies in the internet and the web. From the web, we picked out important features that we were going to reuse. So the idea of identifying documents, but by generalization, things as well, using URIs, and the use of the HTTP transport mechanism to get hold of data, to get hold of representations relative to those identifiers. We described the use of common reused vocabularies to describe data. Okay? In particular, we said that vocabularies can be represented as schema or ontology. Okay? Both of them govern both our expectation for the description of things in RDF, in the resource description framework, and give us means to use a reasoner to give us inference, where we find out, according to the model in the schema or the ontology, certain classes and certain relationships, certain properties, allow us to infer things about the classification and the relatedness of our resources that aren't explicitly asserted, but that can be reasoned. Okay? After that, we talked about a common query language, Sparkle, that says if your data is represented in that RDF form, and possibly if you have even more triples through that inference, you have a common means to say you can aggregate it all, either identifying parts or just talking about all of your data, and make a standard definition of patterns that you want to find in your data, okay, and turn them either into relations, into tables, turn them into graphs that you want to investigate, or turn them into updates over your data, okay, to remove things or to enrich it with more triples. Then we talked about linked data and what it means in terms both of 4 principles and in terms of best practice. And we also talked about the star rating scheme for how you can evaluate how well open data is exposed relative to what the aims of those linked data principles are. We talked about the linking open data cloud, which is all of those open data sets that are exposed according to the principles. Okay? How many there are, how well interlinked they are, for instance. And then we started to talk about application scenarios and how applications build user interfaces on top of that kind of data. Okay? And this is a thread that we'll pick up throughout Euclid to show how those metaphors and how those technologies like annotation and metadata can be used to usefully use data, music, biographical and geographic data that we consider in the motivation scenario to build a novel application. Okay, thank you for listening. As usual, if you have comments, if you have questions, please address them to the Euclid Twitter stream, which is via this Euclid_project channel. Thank you.